Dimitri, and for step one of this project, I'll be focusing on the steel dagger portion. So the goal of this part right now is to design a steel dagger that has an ultimate tensile strength of greater than 800 MPa and a percent elongation greater than 15%. So from the tensile test data that we completed from our previous labs, the U2S, or ultimate tensile strength, of the annealed steel, we got that it's about 270 MPa. And that just means, our starting material is very soft, it's ductile steel, it's pretty typical of a low carbon alloy. So next, what we're gonna do is shape this dagger, so by cold working it. This is a process that plastically deforms the metal without heating it. So the rod's diameter, I just drew a visual over here, is getting reduced from 5 centimeters to 3 centimeters. And in order to quantify this, I use the percent cold work equation, which you can see me using right here. It's simply the initial diameter squared plus the final diameter squared all over the initial diameter squared multiplied by 100. That gives us the percent area reduction. So cold working, it increases the strength but reduces ductility because of the changes in the microstructure. So as the metal deforms, dislocations multiply and tangle, so they just basically block each other's motion, and the steel just resists further deformation. So the predicted strength after cold working is what we did over here. So for low carbon steel, is about 60 to 65% cold work typically increases strength by roughly 60%, which is what I use over here. It's a little bit messy, but this is 0.60. So I took our U2S 270 and multiplied it by 1 plus 0.60, and that gave us 432 MPa. So our cold work steel is nearly double its strength compared to its original, but it still falls short of our 800 MPa target because the steel is very low in carbon. So our annealed steel typically shows about 25 to 35% elongation. With 64% cold work, the standard data shows that elongation drops roughly to 15 to 20%, which means our dagger's ductility still satisfies the greater than 15% requirement. But the cold working improves, although cold working improves the strength to about 430 MPa, it does not reach the 800 MPa goal. So to achieve this goal, what we could do is either use a hard carbon steel, or we could apply a quench and temper heat treatment after shaping. So these treatments can raise the strength into the 800 to about 1000 MPa range while keeping the ductility above 15%.
Hello, I'm Jack, and this is for part 3 of the project. And so in our experiment, we measured the hardness, the tip and the base of aluminum in the steel samples. And for the base, we noticed that for aluminum, the base was at 32.4 for the hardness, and the tip was at 56.6. For steel, the base was at 35.4, and the tip was at 70.8. Basically, this tells us the increase in hardness, tells that the base experienced more plastic deformation or cold work. And cold work hardening happens when a metal is deformed at room temperature. And during deformation, dislocations, like tiny defects in the crystal, they multiply, they start to tangle and intertwine with each other. Basically, these dislocations make it harder for new ones to move, so the metal becomes stronger and harder, but also less ductile. Now, based on that, you can also look at this chart that I made down here, which is microscopically the difference between steel and aluminum. So we have the stacking fall energy, which is lower for steel and higher for aluminum, and this is because aluminum is easier to dislocate while it's harder for the steel. The ductility is lower for steel and higher for aluminum. This is because aluminum can bend and stretch more easily before breaking, while steel gains strength but loses ductility later. For the hardness, we have down here, we have this, that steel is strong, while aluminum stays about moderate. This is because steel locks up faster while aluminum keeps deforming. And for the microstructure for steel, we have that it's distorted, elongated, and it drains with dense dislocation networks, while aluminum is more uniform, partially recovered grains. And this explains why the steel base was much harder to begin with. So basically from this, we can also relate the grain size and temperature, and at the base, the grain becomes elongated and distorted, which strengthens the material or the metal through the Hall patch effect, which is smaller and more distorted grains that resist deformation. If we heated the metal, annealing would cause recovery and recrystallization, which would remove all the dislocations that would occur. Basically, then form new grains, and that would reduce the strength but increase ductility. So overall, our results clearly show the cold work hardening in both aluminum and steel becomes stronger at the base due to dislocation buildup, but the steel hardened because its dislocations are harder to rearrange. Now, if we also look at these two graphs that I created here to help us visualize what could happen, we have the ductility, which is the percent elongation. We also have the tensile strength measured in megapascals by the annealing temperature. We realize that as the annealing temperature increases, tensile strength decreases, ductility increases, which is an inverse relationship. We also have the recrystallization temperature marked here. This could also relate to this graph over here, which is the cold worked and recovered grains, that as soon as it reaches the recrystallization temperature, new grains begin to form, which is clearly shown by this graph. And this graph basically shows us the grain size measured in millimeters by the annealing temperature.
Hello everyone, my name is Alex Medina Fernandez, and today I will be covering point 3 of group 2 for project 2 of material science. Starting with all of our variables, or well, not all of them are variables, but what do they mean? Okay, we'll need them for our equation, so it's important. Na is Avogadro's number, we have it in our calculators since high school. Mb is number of vacancies and is total atomic size. QB is vacancy formation energy in electrovolts. This I put in red because I wanted to tell everyone that is listening that you can find these values tabulated online from reputable sources. So maybe if you need them, you can do that. You can also calculate this value, by the way. K is Boltzmann constant, which is 8.617 times 10 to the negative 5 EB over K. T is absolute temperature. And here is where we start with the actual question. Well, the question is asking us to compare these two and see how they affect yield strength. Well, these two are nothing else but, so this is really the number of vacancies per cubic meter. Here's the formula, and here is the variancy probability. We have to compare these two for yield strength, as I said. Here I outlined two formulas just for ease of work. And then we will put them here to do the actual comparison. We just need to table them like this, to a table, and we'll see values. Okay, and for aluminum it's gonna be lower than for iron. Same with the probability. They are completely related. So if you were to compare this one, and you will know, excuse me. What I was trying to explain really is a higher variancy formation energy will always lower the vacancy probability. We can use this to guide us in terms of who's gonna have a higher yield strength and why. Aluminum is gonna have a lower concentration, a lower probability than iron. Why does this matter? Because that's where, if you have more space within the structure of a material, but it is possible that some defects are integrated into the material in itself in aluminum, and therefore it could affect yield strength in terms, because it's not as cohesive, and yeah, it's a defect or an impurity or and so on. Same goes for iron. If you compare it to any other metal that has a higher yield strength, it's gonna be for similar reasons. This is one thing that I find curious. I like this type of thing. So yeah, thank you for watching, and I hope this has helped you understand a little bit more how yield strength really affects, how it's affected by all of these values. Gives you a better overview. Thank you for watching.